The next step in our look at gravitation is to look at Newton's law of gravitation, so an equation. Now, the easiest way to think of this is that Newton's law of gravitation is to masses as Coulomb's law is to charges. So it's the equation that tells us what the force is between two masses. Now, one of the interesting things about Newton is that he actually didn't see himself as being someone that was particularly important in the development of understanding. He actually, I think there's a quote about him, if something along the lines of, "If I have seen further, it's because I stood on the shoulders of giants." So in other words, a lot of Newton's work was actually building on the work of other scientists. But in doing so, he brought some ideas together that allowed us to get a better idea of what's happening in the universe around us. And he realized that the force between two masses had certain relationship to those masses and the distance between them. And so what he discovered is that the force is directly proportional to each mass. So directly proportional to the masses, and the symbols that we're going to use here, it'll become apparent why we're using capital M and lowercase m later, but we're using those two to represent the masses. So think of capital M as being the larger mass and lowercase m as being the smaller mass. That'll usually be the situation that we're dealing with. So directly proportional to those masses and inversely proportional to the square of the distance between them. So this is another inverse square law. And the way that we write this relationship, square of the distance between, before we get on to the relationship, need to make the point here, it's a square of the distance between the centers of the masses. So not just the edge, it's actually to the center, so to the center of mass. The last thing about this relationship too is that it's always attractive. So the force between the two is always going to be directed towards the two, so each mass will be attracted towards the other mass. So if we combine those relationships, so the force is directly proportional to the masses, so directly proportional to m multiplied by m, and inversely proportional to the square of the distance. Now we're using r here for the distance because if you think about what Newton's work would have been based on, the motion of the planets, you talk about the radius of the orbit, so the radius being the distance between the planets. So just keep in mind here, a radius is a distance, it just happens to be the distance relating to a circle, but ultimately you could use d or r there, it doesn't really matter either way. If we then turn that into an equation, we need to incorporate a constant of proportionality, and so the equation that we get from that, being Newton's law of gravitation, is g capital M lowercase m on r squared. Now that's an important one, it is in the data booklet. Just be aware here too though, that capital G has a particular meaning. It's not the same as any other G. The value of G that we're using here, that is known as the universal gravitational constant. That, by saying it's universal, what we mean is that it doesn't matter where you are in the universe, that value is going to apply. And the value for that, for G, capital G, is 6.67 by 10 to the negative 11. And you can go through and check here that the units are Newton meters squared per kilogram squared. So there's our equation for Newton's law of gravitation. Just want to identify something else here, that if you look at that value of capital G, you notice that it's quite small. So due to that small value, what it means is that the gravitational forces that we would observe, so gravitational forces are only really going to be observable or noticeable to us when one of the masses, or at least one of the masses, is quite large. So by that I mean we notice the force due to gravity because the mass of the Earth is quite large. Our mass isn't that big in comparison, but because the Earth is so big, we can experience that force. So let me just write, e.g. the mass of the Earth. In the case of the Earth orbiting the Moon, both masses are quite large compared to what we think. But we could be talking about, say, the Sun and the Earth. We could be talking about satellites orbiting the Earth, asteroids orbiting the Sun. So as long as one of those masses is quite large, then we can actually notice the forces. These gravitational forces do apply on smaller scales as well, but they're not as significant. In fact, of the fundamental forces of nature, gravitational forces are actually the weakest, whereas the strong nuclear force, weak nuclear force, and electrostatic forces tend to be a fair bit stronger. Now, two other perspectives to take on this idea. While that force of gravitation is responsible for keeping us on Earth, so it keeps us fixed on Earth, that's one way to consider it, the fact that we're so close. It's also responsible for the orbit of the Moon or satellites. Notice though that the value of the force would be different when you've got a greater distance, say, for the Moon or satellites, or the further out that you get. So that force is responsible for keeping satellites, sorry, messed that up. It's also responsible for the orbits of satellites and the Moon. So we'll have a look at some questions in class relating, just calculating the forces of gravitational attraction between different masses. We'll also compare that to the electrostatic forces in some cases as well, just to make that comparison.